In this paper, we present laboratory photoelectron spectroscopy experiments using a high-order harmonic light source.
My name is Huth and I present our experimental setup for the high-order harmonic generation. As driving laser, we use a fiber-based laser system, which you can see on this side. It's an infrared laser with a pulse energy of 14 microjoule and a repetition rate of about 1 Megahertz. With just a few optical components, we guide the laser beam into the ultra-high vacuum chamber where the high-order harmonic generation takes place. The laser beam is focused into a gas jet there, and we can have a closer look at the generation now. In our generation chamber, the gas comes from the top through a capillary, and the laser is focused just at the tip of the capillary into the gas jet. There the generation of the high-order harmonic light takes place, and afterwards there's a monochromator with a toroidal grating where we can select the energy to do photoemission.
To characterize the generated spectrum of the high-order harmonics, we turn the monochromator grating slowly within few degrees and measure the photoelectron signal. We observe a harmonic spectrum from 14 to 40 electron volts generated from an argon jet, whereas from a xenon jet, the harmonic spectrum is narrower but can provide higher photon flux. By using the broad photon energy range generated from argon, we can perform photoelectron spectroscopy on a silver surface at different photon energies.
For photoelectron spectroscopy, we use a time-of-flight spectrometer, and this allows us to map the energy as well as the momentum in two directions, in kx and ky direction. So if we have a dispersion like this, we can also see this, for example, in the ky direction, and then we take a look at slides of constant energy, for example like this, and we measure this on a silver surface.
Using the higher photon flux generated from xenon, we can recognize the D-band complex of silver in a short measurement within 10 seconds. These proof of principle experiments are not significantly influenced by the space charge effects because of the high repetition rate of our light source at 1 Megahertz. In order to compare with other photoemission experiments, we present in this paper an overview. This summary shows the number of emitted photoelectrons per second as a function of the repetition rate of the light source. The red color indicates the energy broadening in a model calculation for space charge effects. Conventional photoemission experiments using high-order harmonics work at few kilohertz repetition rates. Therefore, significant degradation due to large space charge effects has been observed. In our experiments, we work at much higher repetition rate with a moderate photon flux. Our experimental condition can be nearly optimal for photoelectron spectroscopy measurements using a time-of-flight spectrometer. Thank you for your attention.